Hi, I'm Tommaso, PhD student at Graz University of Technology.
And I'm Daniel, also a PhD student at the Graz University of Technology.
Welcome to Bridge the Gap, the physics-oriented podcast,
in which we give insights into various research topics and the life of scientists.
And by the way, if you want to contact us, you can drop a line to our email address bridgethegap@tugraz.at. Hey Daniel.
Hey Tommaso.
How are you today?
Good, thanks.
Me too, but sad news for you.
What's the sad news?
I still couldn't come up with any joke about philosophy.
This disappoints me deeply, Tommaso. You know how much I like them.
Me too. Cannot look at myself in the mirror, but I decided to take it with philosophy.
Good thing you found one after all. As we announced last time, here's the continuation of our previous episode about philosophy and physics.
I have a question which is related to how to model reality, which then relates to quantum mechanics in particular with this interpretation problem. So for example, if I think about how Euclid wrote the Elements, the famous book, right? Mm-hmm. He has this very practical way of addressing the problem because he says okay, let's take a point, which is an entity without extension. But then the way we think of a point, it's something that we can draw on a piece of paper. So we have the model of the point, and then we have, our back to the real world entity that we can use to construct. And so we go on like this. Now I'm thinking, is all the headache that comes from wanting to interpret quantum mechanics, in terms of really real physical objects, coming from this mismatch in terms of what is the model of reality and what really reality is? Because we can experience something. So in an experiment, we have a beam of electrons and then you measure, it deviates up or down, depending on whatever. So this is the physical thing that we observe. And then we go back and we try to describe it in terms of the model of it. So how do you, I don't know if the question makes sense from a physical or a philosophical point of view, but what's your view?
It is certainly a good question whether the mathematical model we dream up is just an efficient parametrization or a description of actual real object. The best example is classical mechanics with its point particles. Super efficient in description, but to the best of our current knowledge, point particles are emergent concepts from field theories. So at that point, we had an efficient description of reality, but it didn't describe the actual reality if we, for the moment, presume that our current understanding is the correct one. But then, of course, people who propose string theory would say, no, quantum fields at the current thing is also not the most fundamental object. So basically, the answer is, at the moment, we don't know. It's certainly possible that these things are the building blocks of reality, but lacking a theory of everything, a fundamental theory of everything, we can never be sure about that. If we would at some point discover a theory of everything, then we can start to actually wonder whether the entities in there are the real ones, are really existing or not. But for the moment, I would call this that the entities which we work with are basically our current best guess, our current best model of that. But given the thing that we don't have any theory yet which predicts the existence of our universe, I have a hard time believing that any of those entities are really fundamental. But then in physics, there are also two major approaches to that. On the one hand, people say, hey, we can do a calculation and we can give numbers and we can do this as precisely as we want and that's it. We don't need to know more about reality. And then there are people, which I admittedly belong to, who says, okay, no, that's not good. And let us figure out what are the actual objects. And that's also the research which has motivated the way in which we wrote up. Because at the moment, we exactly see that you have different ways how you could describe what we call elementary particles. And what you usually get are this set of objects like electrons. But then we see if we want to put it in a mathematical unique frame, these are not really describing the most elementary objects because they are just mathematical auxiliaries. And the real objects look different. And it's only because we are coarse-graining to our common experience that the distinction between both concepts becomes blurry and you often don't need to pay attention.
Yeah, maybe this also demonstrates how difficult things get in philosophy of physics. For instance, when you think about this, what is a main lesson that physics has taught philosophers, right? It's not so easy because, for instance, many philosophers have said it is a priori true that physical objects need extension, right? So it might be true that some of them don't have mass, but it seems, sort of like Descartes and other people thought like it's necessary that physical objects are extended objects. And then you could say, okay, but then now particle physics speaks of point-like particles, right? So maybe this is just not true. But then now it seems like maybe, okay, this point particle concept is somehow misleading, right? Maybe all particles that exist are excitations of underlying quantum fields, and so instance, quantum fields are extended objects, right? And like Axel has said, maybe it doesn't even make sense to say that the fundamental extensions are point-like, but maybe the fundamental extensions are also extended objects. This then gets more complicated with respect to gauge theories. But yeah, it's all of these are interesting open problems. Like, what are the fundamental building blocks of reality? As of yet, we do not know, but we hope to find out.
If you look already at general relativity, it really resolves our idea of space and time as fundamental building blocks. Mainly, you can start to think of reality, or space and time especially, as networks of causal connections, absence of causal connections, rather than that you really associate something like space and time. Space and time become really auxiliary concepts. Time is just tracking, enumerating causally connected objects. And it is just that our perception creates that such an enumeration is something like time. So the more you dig down into the deeper constructions of our theory, the less it resembles anything which you would call reality from your everyday experience.
And this also nicely demonstrates perhaps the history of philosophy of physics, because there's this very famous debate between Newton, or Clarke, who was basically a Newtonian, and Leibniz, right? So Newton, one of the most famous physicists, and Leibniz, one of the most famous philosophers, and they had this debate about the nature of space and time, right? So Newton was a substantialist. He believed space and time are substances. They're objectively there, they exist, they're entities, and they can be understood like a container, right? So there's space, and within space there exists matter, and the space exists independently of the matter, okay? So space is a substance, time is a substance, they exist independently of the stuff that's going on within them. And Leibniz, by contrast, was a relationalist, right? So he thought, no, space and time, they do not exist independently, and they're not substances, they're not objective out there. All that exists is are entities, and the relations between the entities are what we do when we do physics. And space and time as such do not exist, but it's only matter and the relations between them that are relevant. And then it is sometimes argued as that more current physics, like general relativity, somehow supports the Leibnizian view, at least speaks against the view that, or at least it basically contradicts the view, right, that space and time are absolute. Yeah.
But they are still, in general relativity, it's still that they are, substance is said too much, but they are entities, real entities, which have an independent existence of matter. So that is still remaining from the Newtonian view.
Just something from before, because for the interpretation, because I was also curious which one you...
Personally, I don't like those which add additional structures which you cannot access even in principle. That means things like many words interpretations, like Bohmian, quantum mechanics, because they all add stuff which I cannot access. Also things which make, in principle, inseparable bounds, such that I have two separate systems, like the old-style Copenhagen version. I don't like the idea that I need different theories to describe different aspects of reality. I would like to have a neat one theory thing. So I'm in favor of those who try to get rid of the measurement problem and try to create something which is a single theory where I don't have an independent environment, like quantum probability theory, like things which are more evolved decoherence versions, things like that.
Can you elaborate on like decoherence particularly?
Yeah, that's basically the idea that if you start to describe also the environment, so you get rid of the environment, describe the experiment inside the system, then you have many, many particles in the system. And that means you have many, many interactions. And if you have many, many interactions, this will coarse-grain the system such that the behavior will become less and less like a wave with specific properties which look like interference effects and so on. But more and more, the excitations will look classical-like, concentrated. The wave amplitude will be concentrated on small points in space-time, and they move essentially like a classic trajectory, so that classical physics is an emergent behavior of quantum physics. which is a multi-particle effect.
Does this the coherence interpretation solves the measurement problem, or is
it makes it superfluous? So the basic point is the measurement procedure is then just an efficient way of saying, okay, I only look at a part of the system. It also stipulates, of course, that wave functions and structures like that are reality, that we are just bumps in the wave function, and that just because of this coarse graining on large scales, it looks for us classical, and our mind just perceives that in this way. So classical physics really is an emergent behavior. The drawback of that is the system becomes quickly so complicated that you actually cannot calculate it to test.
Because there are too many degrees of freedom,
yes.
You mean? Okay.
But so for very small systems, this looks... So I have one example, for example, in my lecture on quantum mechanics, where I show how this emerges in an extremely simplified model.
Can you say it here?
No, it's basically...
in simple terms.
It's basically you couple two particles.
Yes.
And then you tune the interaction such that the wave function of the one particle, which without the other particle is just a standing wave, becomes more like a Gaussian wave shape by the other objects, and therefore looks like it would be localized like a particle.
Okay.
Which I took over from the excellent book by David's Global Approach to Quantum Field Theory. So it's not my own idea behind that. And but also I don't have a problem to attach additional space to reality, because as I said, basically reality is anyhow only a set of causally related events from the point of view of generativity. So why shouldn't the individual events not have more structure than just a point?
I would have a question a bit more technical. So, for example, before we said, we talked about superposition of states. For example, spin up and spin down, which have, for example, like, I don't know, one half probability, right? So now these numbers, which we call quantum probabilities, or in this case, it will be an amplitude, strictly speaking. Why can we not understand these amplitudes as probabilities prior to the measurement problem? So why do we need the square of these numbers in order to think about probabilities?
The basic problem is it's not a number. It's a complex valued quantity. And therefore, it doesn't have the mathematical properties which you would expect for a probability. That's basically the reason. Of course, you can, even without doing an actual measurement, you can take the amplitude, take its absolute square, and that would give you probabilities as if you would do a measurement at that time, just without the interference of the system, which also means that the time evolution afterwards is different from what you would have if you would do the measurement. But so you can, in that sense, have a time-dependent idea of what the probability would be if you would do no measurement. But the amplitude themselves just is not mathematically, it's a complex number. It cannot be interpreted as a probability in that sense.
So regarding probabilities, in thermodynamics, we also have them, right? So is there any way to distinguish between thermodynamical and quantum mechanical probabilities?
Yes, that is basically the Bell's inequalities. So you can distinguish the classical types of probabilities and the quantum mechanical types of probabilities by certain measurements. Because classical probabilities, like in thermodynamics, that's counting. You're counting number of possibilities. That is always real numbers, which you sum up. In quantum mechanics, these are complex numbers because they are wave functions, which can have interference because of the imaginary parts. So they create different types of probabilities. And that is basically the point of Bell's inequalities. He formulated an experiment which gives you different results, whether you have a counting experiment or whether you have quantum probabilities. Now, first of all, the measurement clearly shows, this has been tested many, many times over, it is not classical probabilities. The second part is quantum mechanics get it right, because just violating that or just saying it's not sufficient to support quantum mechanics. But the numbers which come out are the ones of quantum mechanics. The important thing is it's not so trivial. If you're just looking at two particles or two measurements, you actually can reproduce everything in quantum mechanics with a classical system. You need a sufficiently complicated system, at least of 3 measurements. And I think by now somebody found a way for 3 measurements, but basically for 4 measurements, you cannot reproduce the classical behavior of that. For 3, it is possible in very some obscure cases, but you really need a sufficiently complicated system to make a unique statement. That is also something. Don't try to just argue, okay, I've got it right for two particles. Yes, you can do it. We know that you can do it. You really need to look at sufficiently complicated systems to be sensitive to that.
So Bell's inequality shows that reality is governed by quantum mechanics, or that quantum mechanics gives us a good explanation for reality?
Let's put it that way. There is no no-go theorem which tells us that not a sufficiently complicated theory which is not quantum mechanically could describe all of Bell's inequality. People have invested a lot of effort. Nobody was successful, and quantum mechanics is bang on every number which you can get out of these. So it makes it very likely that it's quantum mechanical. But as I said, there is it's an empirical science. There is as long as we don't have a hard mathematical proof which says the opposite, and of course tomorrow somebody can measure something which kills all of quantum mechanics. Things like that happened before. So, but at the current time, quantum mechanics is the only thing which we have which perfectly describes anything about Bell's equations and perfectly describes all of the experiments which have been done with that.
Yeah, so it's typically said that Bell showed, and the empirical confirmation of Bell's results showed, that local realism is wrong, right? That you cannot describe reality via local realism, which might be something like a hidden variable theories, a local hidden variable theories, and it basically means that something that the thing that Albert Einstein wanted to be true is very unlikely, right? So Einstein was not happy with quantum mechanics, as everybody knows. Often it is said that he was unhappy with the indeterminism because he said it's like God doesn't play dice. But as a matter of fact, what he really didn't like was non-locality. And many people, or some people like Einstein, they believe that quantum mechanics is incomplete. There are some kind what we would now call hidden variables. And Bell showed that if a hidden variable theory is true, then it can only be non-local. So Bohmian mechanics would be a non-local hidden variable theory. So this works. Then you have to pay the price that it's
non-local. But Bohmian mechanics cheats because it adds an unobservable random classical draw into the system. So you still have a complete indeterministic behavior, and one which is classical, but which you can neither observe nor control. So that is how it can get around that.
Can you elaborate a bit more on hidden variables and locality?
Okay, I mean, there are two things. So the hidden variable idea is there are some quantities which a particle carries, which cannot be directly accessed, but which will describe the outcome. And then the idea is, okay, the random results of quantum mechanics are there because at the production time of the particle, these hidden variables are randomly drawn. And then it is just transported locally with these particles over there. And now for the simplest version of that, okay, I just randomly draw these things, then that is exactly what is locality. Because the information is carried locally with the particles, this has a consequence. And that is what Bell's theorem is about. It checks whether this happens. And there the statement is no, it's not possible to locally carry the information uniquely with you to create sufficient randomness. While quantum mechanics does. Quantum mechanics does it in this way because it's not associated with particles. It's associated with the wave function. The wave function is a field which is defined at every space point and every time point in the universe. And if you solve Schrödinger's equation, you do not solve it for now, but you always generate a full wave function for everywhere in the universe. So it's inherently a non-local information. And that is exactly what allows you to do. Now, Bohmian mechanics tricks this by adding an infinite reservoir of particles and couples its random distribution to a field which is determined by Schrödinger's equation. And so by introducing a field and introducing a classical reservoir of randomness, he gets around it by having such a field carrying this information. But in such a way that you cannot back-react to the classical environment. So that is something which exists outside of our access. It's classical, it is there, it is everywhere in the universe. It determines everything, and we don't have any access to it.
So if I'm not mistaken, you don't think that is true?
Let's put it that way. As I said, I don't like the idea of having something which I cannot access in physics. That is the case. It postulates there is something which you cannot access. Also, it is, okay, I take the Schrödinger equation. It literally takes the Schrödinger equation for the wave function part, for the field part, and then adds something on top of that. which is unobservable. As I said, from my point as a physicist, I would like to have something which is, on the one hand, creates observable consequences, on the other hand, why should I add something which is not relevant, which does not create anything new, just create something which I cannot access?
Yeah, so I think Axel here is very much in line with many physicists, because Bowman mechanics is very much disliked among physicists, basically for the reasons that Axel said, right? So you add something.
But I know actually physicists who like it, but it's really also the absolute minority.
I think it's also said that Bell liked it, but I don't know. Yeah, but you add something that is unobservable, so you make the theory more complicated. And as we also said, it's also quite important that Bowman mechanics at the moment, right, is not consistent with special relativity. So we do have quantum field theory, but we don't have a Bowman version of quantum field theory. So this is also one of the reasons why it's not so much liked. And I think in 2013 or whatever, there was a survey among physicists at a conference. So what interpretation do you prefer, right? And as to be expected, most of them said something like Copenhagen, right? So still Copenhagen is very much popular in physics. And some people said, the many worlds interpretation. Some said information theoretical approaches. And I think 0 people said Bowman mechanics. So it's among physicists, it's very much disliked.
But one should add that Bell originally set out that he wanted to disprove quantum mechanics with his experiment. So that was an attempt to find something which shows that there are hidden variables. That's a classical theory. It was never his intention to provide the best. I think Bell's inequality, the violation of Bell's inequality, I think is mostly considered to be the most spectacular proof of quantum mechanics at the current time. But it actually is also a very hard experiment. So it took 50 years before people started to rely on the observations to say, okay, we are starting to see something which is really beyond doubt going in this direction. It's really not a trivial experiment, and they needed very good experimental people to figure out how to do this.
Okay, I think I ran out of questions at least.
Yes.
Which I thought impossible. Which I really thought impossible. But is there something you two would like to mention that maybe it's relevant to this discussion and we didn't have time or we didn't think about it so far?
I'd like to add something that is...
please.
It's a fascinating point that this is still a problem. I mean...
By this you
the
mean
quantum mechanical measurement problem, how the basic formulation is, because it is something which everything relies on. Every part of our modern technology relies on quantum mechanics, and we still don't fully understand its fundamental equations, and that on the one hand puts us a bit on shaky grounds, but on the other hand, it doesn't say that we really make use of quantum mechanics to the largest extent possible, because we have, by not understanding it, probably not fully tapped into it, what it offers us. So it's a bit of a amazing issue that we are willing to work with basically an improvised solution by having just an operative definition rather than a dynamical description of what's going on. So I think there are, even for such theories which are so close to our actual world in comparison to, say, quantum gravity, we don't have a full solution. It's really telling us that we tend to stop too early when asking questions.
I think on this note, maybe we can conclude.
Sounds like a very nice.
Yes, indeed. I want to thank you both again. Thanks for listening.
And hear you next time.
And by the way,
if you want to contact us, just send a mail to bridgethegap@tugraz.at.